1 lecture over periodic trends. So yesterday we looked at how the periodic table can be, well, how it was made and how it can be broken up. Today we're going to look at some of those patterns that both Mendeleev and Moseley said exist in the periodic table. So those patterns are called the periodic law, that elements are arranged by increasing atomic number and similar chemical and physical properties. So basically our periodic table is full of useful patterns, which I love, which means there's even more information in the periodic table than what you see, and I think you guys have learned that so far. In order to understand some of these patterns, you need to understand something called effective nuclear charge. I also will refer to this as nuclear pull. This is the charge felt by the valence electron. So when you're talking about an atom, you know you have these positive protons in the nucleus of your atom. And even though this is a Bohr's model, and that's not accurate, it's the best way I can represent an atom in my two-dimensional space here. So then you have these energy levels, and these energy levels have electrons. And what do you know about positive charge and negative charge? It's that they attract to each other. They want to be near each other, just like the positive end and the negative end of a magnet. So what's happening is these protons here in the middle are actually pulling on these electrons, trying to keep them from floating away. So they have this sort of pull or attraction on those electrons. Hence why, instead of calling it nuclear charge, sometimes I call it nuclear pull. So basically it's the pull of the protons on the electrons. Now when we look at our atoms, and we look at how the pull of the protons on the electrons changes from atom to atom, we can compare two elements such as lithium and sodium, for instance. So lithium has 3 protons in its nucleus. And at its first energy level, it has 2 electrons. At its second energy level, it has 1 electron. When we look at sodium, sodium has 11 protons. 4, 5, 6, 7, 8. Woo, that's a lot of positives that's going to draw. In its first energy level, it has 2 electrons because the first energy level can only hold 2. At its second energy level, it has 8 valence electrons, because the second energy level can only hold 8. And then I should have spaced this out better, but I didn't. In its third energy level, how many valence electrons will sodium have? Just 1. So if you're talking about, in lithium, the protons pulling on this valence electron out here, you see how close in proximity they are? So basically that's 3 positives pulling on that electron that's very, very close to it. Whereas sodium's valence electron out here, even though there's more positives here pulling, look at the distance here. It's much, much greater. So it's a lot less pull, a lot less attraction. If you've ever taken 2 magnets and you hold them together like about this far apart, they'll automatically suck together. But if you hold them this far apart, they don't have as much attraction to each other. And that's the exact same thing that's happening here with the electrons. So as you add energy levels, the electrons, those valence electrons, get further away from the nucleus. And therefore, there's less nuclear charge or nuclear pull. And that's pretty common sense. Now, what if we look at 2 atoms, instead of going down a group, what if we look at 2 atoms across a period? So this time, let's look at lithium and oxygen. So lithium, same thing as I did before, it's got those 3 protons. In the first energy level, it has 2 valence electrons. Or excuse me, not valence, just plain electrons. And in the second energy level, it has 1 valence electron. There's the valence electron. And what did I say? Oxygen? All right, if we look at oxygen, oxygen has 8 protons. 8 in its nucleus. And in its first energy level, has 2 electrons. In its second energy level, it has 8, not 8, excuse me. In its second energy level, it has 1, 2, 3, 4, 5, 6. 6 valence electrons. Sorry, y'all, I'm doing this lecture for the first time cold. I usually record after having done it a few times, so. All little miscues. Hope you're enjoying it, though. So lithium, you can see that the distance between its valence electron and its nucleus is the same, and I'm just going to pick this random valence electron, as the distance between the oxygen valence electrons and nucleus. So the distance away from the nucleus is the same as you go across a period. So because the distance away from the nucleus is the same across a period, distance has no effect over nuclear charge. But I am going to tell you that oxygen's valence electrons feel a much stronger pull by the nucleus than lithium's 1 valence electron. So we know it can't be because of the distance, because as you go across a period, the distance remains the same. So what is it? Why is it that this electron, for instance, and I'm sorry, this is the most ghetto drawing I've ever drawn, this electron specifically right here has a much greater nuclear pull than this electron right here? What's the difference between that electron and this electron? It's the number of protons. So if you look at lithium, you only have 3 positives pulling on that negative. And if you look at oxygen, you have 8 positives pulling on that negative. Now, yes, they do have more electrons to pull on, but they're pulling equally in all directions. So what's going to happen here is as you go across a period, it's actually an increased number of protons, not the distance, an increased number of protons that increases your nuclear charge. So you have really nowhere to write this, but I'm going to put this up there really fast. If you have your periodic table like this, and I'm not good at drawing them, nuclear charge is going to decrease as you go down a group. Why? Because you're adding energy levels. And so your electrons are getting further and further away, so the protons pull on the electrons less. As you go across a period, your nuclear charge is going to increase because you're staying within the same energy level, but you're increasing your number of protons, which means more pull on the electrons. Now, nuclear charge is the basis. This explains every other trend you're about to see. It explains it all. So if you can understand nuclear charge and how tightly the protons are holding on to those electrons, things like size, ionization energy, electronegativity, electron affinity, all these things you're about to learn about in the next few days are going to seem really easy if you just think, well, how are the protons holding on to the electrons? If you know this one thing right here. So now that we have a little bit of an understanding of nuclear charge or nuclear pull, how the protons pull on the electrons, let's start looking at some of these trends, some of these patterns that are in the periodic table. The first one, which I think is probably the most basic, but probably not what you expected, is atomic radii. Now, atomic radii is simply the size of an atom. So your radii is half of the distance of the atom. And actually, it's kind of neat how they measure this, because atoms are so small, you can't just get out a ruler and be like, oh, from here to there, that's the radius of an atom. What they do is they take elements that are bonded to themselves, like, for example, all of our diatomics, hydrogen, neon, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and they take them, they bond them to themselves, and they say, okay, here's one nucleus, here's the other nucleus, and that distance divided by half will be the radius of each one. So it's kind of neat how they do it. They don't actually just measure it, but basically atomic radii is the size of the atom. Now, as we go down a group, like for example, group 1 here, where it's hydrogen, lithium, sodium, potassium, rubidium, cesium, what do you notice happens to the size of our atoms? That's right, they definitely get bigger. They increase in size as you go down a group, which is probably what you expected, right? We're adding energy levels. It's like adding layers onto our onion. It's definitely getting bigger. But as you go across a period, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, or any of these other ones, for instance, what do you notice happens there? They decrease in size. They get a lot smaller, and that's probably not what you expected to happen. You're probably like, oh, well, they have more protons, more electrons, they're going to get bigger because there's more stuff involved. But because of nuclear pull, and because as you add protons, it pulls the electrons in tighter, they actually get smaller as you go across a period. So think of it like a hug. So you and your friend are hugging. You don't really like this friend. You give them kind of like, you know, the hug where your arms are really far apart. You know, the butt out hug where you don't want to touch them too much. Okay? You don't have a very strong attraction for this person, so you're not very close together. But if you're really strongly attracted to somebody and you hug them, you're going to grab on, you're going to squeeze in tight, you're going to press your body against theirs nice and tight, and you're going to make a much smaller space. And that's exactly what happens as nuclear pull increases. As nuclear charge increases, it's pulling in tighter on those electrons. So now that you know what atomic radius is, let's mark it on this chart. So as we go across the period, atomic radius decreases. It gets smaller. As you go down a group, it increases. It gets bigger. So what would be the biggest atom on the periodic table? Use the periodic table on the wall. Figure it out. Which one would be the biggest? We know it gets smaller as it goes across, so it's going to be on the left-hand side, and it gets bigger as it goes down, so it's going to be francium. And it's true. This is absolutely the biggest element on the periodic table. What about the smallest? Well, it gets bigger as it goes down, so we're going to be at the top. It gets smaller as we go across. So helium. Helium is our smallest element. So if you want to put this general trend, you could say, you know, always have this arrow small to big. So this is the trend of increasing in general. You don't have to draw that diagonal arrow, and that's increasing. I don't know why it made 2 lines, but so that's atomic radius. That is the size of our atoms. So what about ions? Okay, we spent the whole last 2 units talking about atoms, talking about ions, how atoms have equal number of protons and electrons, and ions have different number of protons and electrons. So what about them? Let's draw lithium again as both its elemental form and its ion form. Now, lithium's a metal, and we learned yesterday that metals form cations, because metals have 1, 2, or 3 valence electrons that they want to lose, and if you lose electrons, you're losing negative, you become positive, and cations are positive. And throw that in there. So lithium has 3 protons, 1, 2, 3, and over here when it's an ion, how many protons is it going to have? Yeah, exactly the same number. You don't change it because it's an ion. You don't even change it when it's an isotope. It's going to stay the same. Now, lithium, like we said before, has 2 electrons in its first energy level, and in its second energy level, it has 1 electron. So there's its elemental form. And it told me it's going to form a cation. So it's going to lose electrons to become positive. How many electrons is it going to lose? Well, how many valence electrons does it have? It has 1, right? So So it's going to lose one electron and become lithium with a +1 charge. Just looking at that, the element versus the cation, which one's bigger? That's right, the element. So when you're talking cations, they are always smaller than the neutral element. Why? Why is that? Because when you become a cation, you lose your outermost energy level. You lose an energy level, which automatically makes you smaller. It's like peeling off a layer. So positive ions are always, make sure you circle in your notes, smaller than its neutral atom. Let's look at fluorine, okay? Fluorine has 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it has 9 electrons in its elemental form. As an ion, this one forms an anion. Because fluorine is a nonmetal, so it tends to gain electrons to become negative. And if it has 7 valence electrons, how many electrons will it gain? Get 8, 1, forming an overall -1 charge. Now when you look at this, it's hard to tell, right? You can see that both of them have 2 energy levels, so it's not about the size of the energy levels. So let's compare our protons to our electrons. Let's look at that nuclear pull, that thing we were just talking about. In this case, I have 9 positives pulling on 9 negatives. Okay, that's a 1-to-1 ratio. On this side, I have 9 positives pulling on 10 negatives. I have more electrons than I have protons because it's a negative anion, which means the pull of these protons on these electrons will be less. Imagine it like a kindergarten classroom. You have 9 teachers to 9 students. Are those kids going to be well behaved? Yes, they are, because one teacher can look at one student. They're going to do exactly what they're supposed to do. Whereas if you have a kindergarten classroom that has 9 teachers and 10 students, one student is not getting watched by a teacher. Okay? So the average behavior of those kids is going to be a little bit looser, right? They're going to chill. They're going to do some things that maybe they shouldn't. So for an anion is always larger, make sure you're circling that in your notes, than its neutral element or atom. Remember, an atom is just a piece of an element. This is because you decrease the nuclear charge. You decrease the nuclear charge when you add electrons. So that's a pretty sweet deal. If you can remember, cations are positive, so they're losing electrons. They're losing energy levels. They're obviously going to be smaller if you're losing things. Where anions are negatively charged. They're gaining electrons. You're gaining electrons to decrease that nuclear charge. You're going to be bigger. So let's look at this trend as a whole. Ionic radius, which we need to make sure we define what that is. Well, if atomic radius is the size of an atom, this is simply the size of an ion. And because this side of the periodic table, the left side, are metals that form cations, we have to consider them differently than the right side of the periodic table made of nonmetals that form anions. Keeping in mind that we do not look at noble gases. And why is that? Because we're talking about ions, and noble gases are happy with their full octet, and noble gases do not form ions. So when you're looking at metal cations, metals that are cations, you're going to always increase as you come to this corner. So just like before, the francium ion, Fr+1, is the biggest possible ion you can have. So this is the exact same trend. I know I'm writing it a little bit differently than I did the last one, but it's the exact same trend. This is your biggest one in this bottom left-hand corner. And in this case, not helium, but the fluorine ion will be your smallest ion. So these metals will go in this trend. These, non-metals will go in this trend towards fluorine. So, which is bigger, the cation or the neutral atom? The neutral atom will always be bigger than the cation. Which is bigger, the anion or the neutral atom? The anion will always be bigger. And here's a trick I learned. I think this is kind of neat. When you're comparing an element to its neutral form, or you're comparing elements, or ions, to each other, the trick I always say is the more negative, sorry, this smartboard went crazy for a second. The more negative the ion, the bigger the ion. So if you have something like S-2 versus Cl-1, I don't even need to look at a periodic table. Who's going to be bigger? S-2, because -2 is more negative than -1. Might be easier to think of this as the more positive you are, the smaller you are. I like that, actually. I've never done that before, but we're going to look at it this way. The more positive, the smaller you are. And so if you're looking at cations and you want to look at Na+1 versus Mg+2, and I asked you which one's bigger, you have to make sure that you always know what's being asked. The answer for which one's bigger is the sodium, because +1 is a more negative number than +2. Or you can look at it the other way. +2 is more positive, so this one's smaller. Hope that didn't confuse you, but it's just kind of a little trick for the trade. If you're comparing things that are not, they have the same charge, for instance, something like sulfur with a -2 charge versus oxygen with a -2 charge, you're like, oh my gosh, how am I going to know which one of these is bigger? You're going to have to go back to that periodic table, right? So if oxygen's here and sulfur's here, and it gets smaller, it decreases going up and decreases going down. You know, fluorine is the smallest. Which one is closest to fluorine? The answer would be oxygen is the smaller one. If I'm asking which one's bigger, the answer would obviously be the opposite, sulfur. So when you're doing your homework tonight, you always have to make sure you understand what it is that they are asking before you start circling things. Are they looking for the bigger one or the smaller one? So your notes should be filled in. This video is already online. So if you need to go home and watch it again, you can. Your notes are 1 through 25. That bottom section, you might need to use your notes from yesterday to fill out. And I will, if you're in my class, Miss Nelson's class, I will be back tomorrow, and I'll happily answer any questions or confusions you guys have over this. Homework for the rest of the period, sit quietly, work individually. Good luck.